So, in today's lesson, we're going to be taking a detailed look at how to read in the contents of external data files into R in a form that R can process. This, in general, is of course the first step in any data analysis pipeline. We read in the data. And once we have done that, then we can start doing manipulations, we can start doing exploration of the data, we can make figures, we can run models, statistical or otherwise, and then, of course, based on the results of those models and figures, we might update the kinds of manipulations we do on the data. We might update our models, we might update our figures. So data analysis is an iterative process that goes through these cycles multiple times, but this cycle always begins with reading in the raw data in the first hand, and that is what we're going to be taking a look at today. One small disclaimer, here we will be focusing strictly on tabular data, that is, data that can be arranged in rows and columns. Now, that is probably the most common kind of data out there, but you should be aware that other types of data do exist. For example, if you're interested in phylogenetics, then you probably know that most phylogenetic data, or at least much of phylogenetic data, come in the structure of some sort of tree because of the natural tree-like structure of a phylogenetic diagram. Those do exist, those are good, but here we will be strictly focusing on data that come in the form of tables. How are data usually stored? Possibly the most popular format is of course some sort of spreadsheet, and I guess the most popular one in existence right now is Excel spreadsheets. So while those are very popular and very accessible, I would still advise one not to use them for serious research. In fact, it is better to use simple, plain text files instead. Now, that might be a strong claim, you think, so let me try to substantiate why I think that this is the case. So first of all, in order to be able to read in and save Excel files, one needs proprietary software, namely Microsoft Excel. One needs to buy that, and maybe not everybody can afford it. So that is one disadvantage of using Excel, not to mention that this again runs against the basic principle of science I was mentioning before, which is that we are aiming for transparency, we are aiming for using software that is fully open source so that we can look behind the scenes and know what it is actually doing. Second of all, plain text files will never go obsolete, at least not in the foreseeable future and beyond, not in our lifetimes for sure. So it will never have backward compatibility issues. We will always be able to use it. If today we save data in plain text files, then in 60 years somebody will be able to open them and use them just like they can today. That is decidedly not the case with proprietary software such as Excel. If you doubt what I say, try to open an Excel spreadsheet that was saved 30 years ago with a modern Excel and you will see what I mean. Now, the final advantage of using plain text files is that in a plain text file, everything is explicitly written in. When we use Excel sheets, then there is a lot of hidden formatting, or irrelevant formatting rather, that we can use. For example, give different colors or different font sizes and shapes and weights to the different cells that we're using. None of those carry information in terms of the data. They might carry information for other human users who are looking at the data, but when we are working with data inside the computer and processing it using R, we don't care about that. And using simple plain text files suppresses the temptation to try to rely on these features that are really not necessary at all. In fact, they are in the way and hinder our usual general workflow. Okay, so if plain text files are what we're going to be using, how should we represent data using those plain text files? Now, over the years, there have been many conventions developed for doing this. The thing that we're going to be doing here, and the most commonly used one, are what are called delimited files. And delimited files are simple plain text files where the data in the different columns are separated by some given character that we agree upon, such as a comma, such as a tabulator, or there are other options as well. We're going to be seeing examples in just a bit. Now, before doing so, let me first introduce to you a data set that I'm going to be using again and again in this course to illustrate ideas in how to analyze data. So this data set is actually one of land snails of the genus Nasiotus, and the data come from the Galapagos Islands, in particular from Floriana Island in the Galapagos. So on the right you can see some photos of these beautiful land snails. Photo credits, by the way, are due to Professor Christine Parent, who is incidentally also the person who is spearheading the collection and curation of all this data set. So I'm going to be relying on Professor Parent's data in here. So let's take a quick look at what these data look like. So each of the rows of the dataset will represent a single snail individual that has been collected. And the columns, let's take a look at those. There are 4 different columns in the dataset. The first column is habitat, and that can be either humid or arid. So those are the 2 basic types of habitat that these snails inhabit. The second column is the name of the species. Again, the genus is always Nasiotus, but within the genus we need to know which species we're talking about. That is what that second column tells us. The next column, the third one, is the size column, which is a measure of the absolute size of the shell of each snail individual. Do not worry about what units this is being measured in. It's some sort of measure of total volume. The point is, the larger or the number is, the larger the shell of the given specimen. Finally, the fourth column is a measure of the shape of the shell of each specimen. So the way to think about this, again, don't worry about the units. It's just that if these shape values are small, and by that we mean negative, then the shells are more round and bulky, whereas if these values are larger, that is positive, then the shells are more slender and long, like you can see in the pictures. Like if you look at the topmost snail on the pictures, then you see that that's more of a round, bulky shell, whereas if you look at the bottom individual, that's a long, slender shell. So the first one would have a negative value for its shape parameter, whereas the final one would have a positive number. Alright, so after this basic description of the data, let's see how we can represent them using delimited files. So here is how we would represent it with what is called a comma-separated value file, or CSV for short. By the way, you can download this data file using the link at the bottom of the slide. If you download that file, you will get a compressed zip file, so be sure to extract it, unzip it, and then you will get a file that's called islandfl.csv in there. The .csv is just an indicator that this is a comma-separated value file, of course. So the contents of the file, if you look into it, looks just like what you see on the slide. So the first line of this file is a header that tells us what the names of each of the columns are, and the entries are separated by the comma character, which is why it is of course called a comma-separated value file. And then in the subsequent rows, you see the corresponding data. So you see, for example, in the second line of this file, we have humid, which is referring to the habitat. And then there's a comma indicating that now we're up to the second piece of datum in that row, which corresponds to the species, which in this case is Ustulatus. Then again, you have a comma, and then you have the size parameter, which in this case would be 17.088. And finally, after yet another comma, you have a shape parameter. In this particular case, that is minus 0.029. And so on and so forth. So this is how data can be structured in a delimited file. We just write out the data entries and separate them with commas, and write entries of new rows in different lines. Now, there's nothing forcing us to use the comma as the delimiter, and in fact another very popular choice is the so-called tabulator-separated value file, or TSV file. So in these files, a single press of the tabulator key is what separates different items in various columns. So here's an example. Again, you can download the file from the link in the bottom of the slide. And once you extract and open it, you will see the exact same thing that you see on the slide right now. Again, just bear in mind the different gaps between different items in the same row do not refer to various numbers of spaces. They instead refer to a single press of the tabulator key, and wherever that aligns the different items is where they go. Okay, so otherwise this is completely equivalent to a comma-separated value file, and often which one we use is a bit of a question of taste. In fact, both are very popular. Now here's an example that is not popular and is not standard, but I've included anyway for the sake of example, which is a %separated file where the delimiter, the character that separates out entries in different columns, is the % symbol. It works exactly like a comma-separated or tabulator-separated file, and you are more than welcome to use it in principle. In practice, people don't usually use this. People usually rely on comma or tabulator-separated files, but in terms of the principle, to understand it, just be sure that you understand that this is, of course, a possibility. In fact, any character can be used as the separator. The one thing to pay attention to is not to use a character that you might use for other purposes. For example, in this particular file, if you would choose the period, the dot, to be the separator instead of the % symbol or the comma or the tabulator, that would not work well because we already use the period to denote the decimal point. And so both the computer as well as the human users would get confused as for when we see a period, does that actually refer to a decimal point or to the delimiter of various columns. So for that purpose, just be sure to use delimiters that you do not use for any other purpose. Alright, so with this, let us turn into how do we actually read in delimited files. So now it is time for us to turn to the tidyverse suite of packages. If you do not yet have it installed, please, this is the time to do so then. Install .packages and then in parentheses and quotes, tidyverse. Do that. Again, it can take its precious time to install, anything from 5 minutes to more than an hour, so just be sure to give it some time. If it works on it for a long time, that's normal, so be sure to have it installed on your system. And once you have it, then you can load it with this function called library. And then in the function library, note the lack of quotation marks in calling the package. So just say library tidyverse, and then if you press enter in the console, if that's where you put it, then you will execute this. Or if you use the text editor, then just press Control Enter after typing this and it will be sent to the console for processing. If you do so, then you will see something like the following. A message appears that looks like this. So first you see this thing attaching core tidyverse packages. So the thing you should know is that the tidyverse consists of many packages, around 30 of them, but by default only a handful, namely 9 of them, get actually loaded. And those 9 are displayed here. You know, they have the names of dplyr and forcats and ggplot and so on and so forth. Some of these we'll be using, many of them in fact, throughout this course. Some of them we will not be relying on much, but what we're going to be relying on today, what we're going to be learning about is this package, the readr package. That is the part of the tidyverse that is responsible for functions and utilities that allow one to read in files from disks. Apart from this, there are a bunch of messages written out. You can see them if we scroll down a little bit. Do not worry about this at this point too much. All this is saying is that some of the functions that are getting loaded with the tidyverse have the same names as functions that are already built in and ready for you to use. So one has to do something to resolve that conflict if one uses those functions. Do not worry about that. This will not affect your work at this stage. Okay, so the function we use to read in delimited files is called read_delim. And again, it is part of the tidyverse, in particular of the readr package. Now, what are the inputs to this function? It has several of them. It's a very flexible function, but the two important ones that we need to focus on are the file and the delimiter. The file input is the name of the file with a path, if needed, given as a character string. Now, if you set your working directory to be pointing to where the file is which you want to load, then of course you do not need to bother with the path. We've talked about that earlier in this course. Otherwise, if the file is elsewhere, then of course feel free to use a path to access it. The second input is the delimiter, which again is given as a character string, but it should contain only a single character, namely that one character that delimits the columns from one another. So it could be a comma or a tabulator or a % symbol, whatever is being used to delimit them. We're going to be seeing examples shortly. And finally, readdelim, apart from these two inputs, takes other options as well, and we will see some of them quite shortly as well. I just want to make one little note here. There is another function that is very similar to read_delim, which is read.delim, which is part of base R, so it's accessible even without loading the tidyverse. Now, as it happens, the read_delim function in a way is trying to be an improvement over the read.delim function. In my opinion, it succeeds in doing that very well. Therefore, my recommendation is simply to not use read.delim and instead just stick to read_delim. So let us see finally an example of reading in a file. Let us read in the islandfl.csv file that we downloaded earlier. Again, as a reminder, the link is at the bottom of the slide, so you can get it if you haven't done so. How would we read in this file? The way we would do that is, as you see on the slide, we give the name of the file, island-fl.csv, as a character string, so that's why it is in quotes. And then we give the delimiter, which we set equal to the comma, again in quotes, because it has to be a string. This assumes that the working directory is set to whichever folder is containing the file islandfl.csv. So if the working directory is elsewhere, then either adjust the working directory to wherever the file actually is, or else be sure to prepend the file name with a full path to access the file. Maybe this is also a good point to mention something, just a little warning. So you see that the extension to the file here is .csv. That makes sense. This is a comma-separated value file, and those very often have this extension. But you should keep in mind that it is by no means forced to have that extension on comma-separated files. So in other words, it is perfectly possible for a comma-separated file to have a different extension, say .txt for just text, or .dat for data, or whatever else. And conversely, in principle, if this was a tabulator-separated file, it would be perfectly possible to still give it the extension .csv. While I'm not saying that those are useful or nice things to do, they can happen either by accident or for other reasons. So the only real surefire way of knowing what your delimiter is to actually open the file with a simple text editor. That can be the text editor in RStudio itself, for example. So if you open the file there and just look and see what the delimiter is, that is the one sure way of deciding what you have to use. Anyway, going back to this function, what happens if we actually execute it? So if we do that, then we first of all see a message that looks like this, which can look a bit intimidating, but actually it's quite simple. So let us go through it bit by bit. First, you see how many rows and columns the data have. So you see 223 rows, 4 columns. As we've discussed, each row corresponds to a single snail individual, so this means that there are 223 snail individuals recorded in this data. Then you get some information about the columns. In particular, what is the delimiter separating them? In this case, that is of course the comma, because we are dealing with a comma-separated value CSV file. And then you get information about the types of the columns. We're going to be talking about this later as well, but for now, just bear in mind that CHR stands for character string. So that's just the shorthand version of showing that there are 2 columns that have the type of character string, and those are the habitat and the species columns. And similarly, there are 2 columns that have the type of DBL, which looks intimidating and cryptic, but actually it simply stands for double precision numerical value, which simply means number. There's some computer science history here for why this is the name. Don't worry about it. Whenever you see DBL, it stands for just numbers. And the reason it's called DBL is because of double precision numerical values. And you see that the size and shape columns are both of type number, so they are double precision numerical values. And the rest of this is just a bit of a message. If we go down here, you see that you can get more information on the columns and that you could do something to suppress this message. You do not need to worry about those things right now. After this message comes something much more important, namely the actual data. And this is what it looks like. So you see in the first line a comment line which says a tibble 223 times 4, which means this table has 223 rows and 4 columns, and in the tibble word here, no, that's not a typo. Tibble is the name of the data type that represents these kinds of tables in R. Incidentally, if you hear the word data frame said anywhere, that essentially means the same thing. Again, a data frame is the original concept that was developed in R, and the tibble is sort of the tidyverse improvement on top of the concept of a data frame. So, not that that's particularly important. The thing to remember is that when you hear the word tibble or data frame, just think of the equivalent of a spreadsheet in R. There's going to be another lesson which will discuss tibbles in detail, so I'm not going to discuss them in detail right now, just let you know the basics of how to read them. So first of all, you see that there is the header information with the names of the columns, habitat, species, size, and shape. Below that, you see the types of each of the columns in these angle brackets. So CHR again stands for character string and DBL for numerical data, double precision numerical values. And then you see on this slide the first 6 rows of this dataset. If you run this code in your own RStudio, you will most likely see the first 10 rows. That is normal. I have opted to show you only 6 because then it will fit on the slide comfortably. But you see on the final line down here in a comment line that it says that there are 217 more rows to make up for the 223 total ones. So 217 plus the 6 that are actually displayed on your screen. Or in your case, if you will be looking at it in your RStudio, you will probably have 10 rows displayed, and the information will say that there will be 213 more rows. Incidentally, this is normal behavior that only the first little bit of the data are shown. That's just because the system doesn't want to overwhelm you by dumping the whole dataset at you. There are ways of displaying the whole dataset. We will be looking at those again in later lessons. The point is, they are there, so they're accessible. It's just not shown to you just so that you're not overwhelmed with all the information. Okay, so we've just seen how one can read in a comma-separated file. How do we read in a tabulator-separated file? It's exactly the same thing, except when we read in a tabulator-separated file, there is a special way of specifying that the delimiter is the tabulator. Namely, when we specify delim, we do not say that it is equal to, quote, a single press of the tabulator character and then close the quote. That is not how we do it. Instead, within the quotes, we write a backslash and the letter lowercase t. And that character, or this combination of 2 characters, stands for, it represents a single press of the tabulator key. So really, it represents a single key press, so that's why it really actually stands for a single character, and this will allow us to read in a tabulator-separated file. Now, this particular file that you see here contains the exact same data as the comma-separated file that we've seen before. Again, the link you can see at the bottom of the slide. It contains the exact same data, it's just that the separator is different, the delimiter is different between the columns. So therefore, if we load this tabulator separated file, we'll get the exact same output that we had before. And then the exact same thing is true of %separated files, if that's what we want to do. I want to emphasize again, this is not a standard file format, so usually you will not find this and usually you will not want to use this, but I want to illustrate this as an example that in principle any character could be your delimiter. So if you want to read in this .psv extended file standing for %separated value, then you can do that. You just have to specify the delimiter as the % symbol, and again the file contains the exact same information as before, and therefore the output is exactly the same as before as well. Now, you might be wondering what happens if you try to read in a file with the wrong delimiter. For example, if you take the %separated value file that we just looked at, but you specify the delimiter as being the comma in the readdelim function. What happens then? Well, let's see the output. It is quite instructive. The message that you get immediately tells you that there are 223 rows in the data, as we know, but there's only a single column. Why is that? Well, if you think about it, the reason is simple. It's because the system is looking for a comma in every single line to see where one column ends and another begins, but since there are no commas anywhere in any of the lines, the system just concludes that, oh, that must mean that there's only one single column in this data set. So that is why. And then this column is read in a very weird way. The name of it is habitat percent species percent size percent shape, because the system doesn't know any better. And if we look at the actual data and its output, you'll see that it has one single column which has this silly name, habitat percent species percent size percent shape. It's of type character string, and its entries are all the entries that we know really should go into the data mushed together into a single character string. So the numbers you see in the entries are not actual numbers. In this case, they're treated as text. One more very small comment. You see these backward tick marks around the name here. Now, if you recall, several lessons ago we talked about this and mentioned that we can always use backward tick marks to override default naming rules in R. Now, the default naming rules only allow for, if you remember, letters, numbers, period, and underscore. But this column name here, that one, it has the percent symbol in it, which is not a standard character. It would not be allowed otherwise, but it is of course allowed if we put it in between the backward tick marks, which is exactly why it is included in that way. So this is just a cautionary example to show you that you should get the delimiter right, because if you don't get it right, the system will not necessarily throw an error. It will just read in the data wrong. So when you see a file like this, you look at it, you see that actually it should be the percent symbol that's the delimiter, and then you have to specify it in that way as well. Next up, let's talk about what happens if a file is written in such a way that it doesn't have a header. So far, we've been dealing with files whose first line has been the names of the columns and the actual data only follow afterwards. What happens if we have a data set which does not work that way? And here is an example. Again, as usual, you can download the file from the link in the slide, at the bottom of the slide. And if you do that, what you'll see is the following. This file is exactly the same as the ones before, except it lacks the headers. It lacks the first line in that table. So now you can see that the table is being read in, and it has only 222 rows instead of 223, and it still has 4 columns. And you see, if you look at the names of the columns, let me highlight those, here they go, that something is wrong. Namely, that the actual data have been assigned as the names of these columns. Well, what can poor system do? The system simply looks at the file, looks at the first line, and whatever is there, those will be the headers. So the poor computer doesn't know any better. It just took the first row of data and assigned them as if they were names. Again, by the way, incidentally, notice the backticks around these names because they contain characters that otherwise could not be parts of names. Okay, how do we fix this problem? Actually, it's quite a simple fix. We just have to add another argument to the readDelim function, namely call names equals false. Let's see how this works in practice. So we do everything as before. We read in this file without the header. We specify the delimiter, but then we also specify the call names equals false argument. And this will tell the function not to treat the first row of the data as if they were the column names. Instead, it will fill those names out with its own scheme. It will call them x1, x2, x3, and x4, as you can see. Okay, that is very nice and good, but you might just think that x1, x2, x3, and x4 are not the most imaginative names that these columns could have. So is there a way to change these names? As it turns out, there are actually multiple ways of doing that, but the one that is very straightforward to do within the readDelim function is to use the call names argument to actually specify a vector of character strings. And if we do that, then those character strings will become the names for the columns. For example, if here we read in the file just as before, but we specify the call names argument as a vector of the strings habitat, and then species, and then size, and then shape, then those will become the column names. And as you can see, now the table is exactly as before. It has 223 rows as it should. The names of the columns are fixed and everything is all right. So it turns out that CSV and TSV formats are so popular, in fact, that there are convenient shorthands for reading them in. In particular, instead of writing out readdelim and then giving the file name and specifying that the delimiter is a comma, one can use another function that is called read_CSV. And this function assumes that the delimiter is going to be the comma, so we do not need to specify that. All we need to specify is the name of the file. And it's exactly the same thing with the read_tsv function that assumes that the delimiter is a tabulator, so we do not need to specify that, we just specify the name of the file that we want to read in. To give an example, we had our earlier comma-separated value file, and we can read that in instead of with readdelim, just with read_csv. And notice that we specify the file name, islandfl.csv, but we do not need to specify the delimiter anymore. Incidentally, the same thing would have happened if we had read in the tabulator-separated file with its helper function, the read_tsv function, and we would have gotten the exact same output that we can see on the screen right now. Final thing for today, as I mentioned in the beginning, Excel files are very, very popular. So while I discouraged you from using them, you might need to read them in anyway because other people might store their data in that format. If that happens, don't panic. There's a package called readxl, spelled with an X and an L, which is actually part of the tidyverse, although not the part that gets loaded by default. Therefore, you have to load it explicitly by invoking library readxl, like you see at the top of the slide. Once you do that, you have access to the function readxl. And readxl works much like readdelim. You specify the name of the file, but then you do not need to specify a delimiter because Excel files are not delimited files. They use their own internal system for delineating which piece of datum goes in which column. So you do not need to do that. However, one thing that Excel files do have sometimes is multiple sub-sheets, so multiple sheets that the Excel file has. And then you can specify which of those sheets you want to load in. Here, as you see, I specified sheet equals 1, which means I load in the contents of the first sheet. In fact, this particular file only has one sheet. Again, the link at the bottom of the slide leads you to the file so you can download it and see for yourself. Incidentally, if there are multiple sheets in an Excel file, then you can not just pick them by number, but you can also pick them by name. So you can specify the name as a character string and you can pick it out that way as well. And then if you look at the contents of this file, you run this in R, then you see that it contains the exact same thing as before. So now this output is in exactly the same format and it's exactly the same thing as we've had with read CSV, read TSV, and all the other methods when we were reading in delimited files instead. So one thing you could actually do after loading these files is to save them in some sort of delimited format, and we will learn how to actually do that in the next lesson. So until then, see you again next time around.